Yes.
But it's
What
like
is
those-
the government,
it's like-
what's the government talks about?
It's like one of those ones you see at the hotel.
Exactly.
It just falls off the edge and comes back up or something.
Why
No one
can't,
knows.
why haven't we seen those giant walls apparently?
It's not to scale.
Not-
That's
I've seen that quote way too many times. I'm not sure to show me. This diagram is not to
Not to
scale.
scale,
Yeah.
So you're telling me the Earth
Yeah.
isn't half the size of the sun?
You're telling me. The Earth is not an inch away. They orbit in the
Dr. Harmon's right.
Yes. So what's the interstellar dust made of? So again, the particle sizes are like a micron or thereabouts. So it's about the size of the particles in cigarette smoke. Not that I'm encouraging smoking or anything, but it's about the size of particles in cigarette smoke. And cigarette smoke has a kind of bluish cast to it because of the fact that it's scattering short wavelengths more than long wavelengths. That's why cigarette smoke can be kind of bluish in color when it's coming off the end of the cigarette, but when somebody inhales and breathes out, it tends to be whiter because then they've got more of the little vapor particles, which are larger, and the effect isn't as big in that case. So, composition of interstellar dust, thought to be silicate grains and graphite grains. And as we'll see when we talk more about stellar evolution, we think that the carbon, the graphite grains form in the outer atmospheres of low-mass stars at the end of their lives when they undergo what's called dredge-up. So they're creating, from helium fusion into carbon in their cores, there are some times when they have what's called a dredge-up, where convection reaches deep down into the interior and dredges up carbon that's been created in the core. And when it gets out to the surface, where it's cooler, it condenses in little grains. And these low-mass stars have strong stellar winds because they're very distended at this stage of their lives. And as a result, their outer layers are not held onto very tightly, so they tend to blow off into space, and we think that that disperses grains formed in their atmospheres into the interstellar medium, and is the reason why there's the dust there, is what it comes down to. So, pretty interesting, I think. Alrighty. The predominant component of the ISM is hydrogen gas. So now we're going to have an exciting list of what the ISM is made of. So, ISM stands for interstellar medium. Yeah. The predominant component of the ISM is hydrogen gas.
Interstellar moths.
Yes.
internal soccer balls.
Internal soccer moths.
So about 70% by mass, which if you think about it isn't all that surprising because the not dark matter in the universe is about 70% hydrogen by mass. That's kind of, the composition chemically of the universe as a whole. So, H1, atomic hydrogen, right? Because the Roman numeral is one more than the number of electrons that have been removed, which means this is neutral hydrogen. Is observed via 21 centimeter radiation. So that means I need to get this guy fired up so that I can show this transition here. A picture of what's going on. All right.
Can't get over that name.
What is it, Oberpfaffenhofen, right? Yeah, that's a good German.
Town in Germany.
Yeah,
Oberpfaffenhofen.
yeah, we're gonna go to Oberpfaffenhofen.
Oh,
Yes. I hope that we're gonna go to Oberpfaffenhofen.
I'm hoping we're going over Oberpfaffenhofen.
Yes, this could rapidly degenerate.
It's only the first hour.
Yeah. Okay. Let's see.
I thought we were gonna make it.
So we'll show a little cartoon of this transition.
There's a globe that the entire Earth is holding.
The entire Earth is Poland.
Yeah. It says the Earth is not round nor flat. It's Earth is
It's a what?
It's just a globe that the entire, all the land on Earth is just Poland.
Poland.
Zoomed in view of Poland.
Yeah, that makes perfect sense. Okay.
A little bit supposed to be.
Welcome to Poland.
All right, so here's how 21 centimeter radiation is produced. That's very much a radio wavelength for sure. It's like 1400 something megahertz. So sometimes it's given in terms of the frequency, but 21 centimeters is easier to remember. The WOW signal at Perkins, the candidate for being a signal from an alien civilization, was at this wavelength, 21 centimeters, because the telescope was actually being used to study 21 centimeter emission from atomic hydrogen in the interstellar medium. And the thing is that if we were trying to tell alien radio astronomers, well, alien civilization that we were here, the kind of thing you might do is transmit it at 21 centimeters, because you figure the aliens are, if they're studying the galaxy at 21 centimeter wavelength, they'll hear your signal that way. So you don't just broadcast at some random wavelength, you broadcast at a scientifically interesting wavelength so that folks conducting science, I don't know if aliens should be called folks, but whatever, folks, alien folk conducting science would see your signal as a result of that. So here's the idea, is that in the hydrogen atom, because of quantization, the spin of the proton and electron can be either parallel or anti-parallel with one another. And it turns out that the parallel configuration is the higher energy configuration, and the anti-parallel configuration is the lower energy configuration. And there's a very, very slight energy difference between them. 21 centimeter photon has a very, very low energy, even by atomic standards. There's a very slight energy difference between them. But there is an energy difference, and when you go from the high energy transition to the lower energy transition, the change in energy, if it's a spontaneous transition, is emitted as a 21 centimeter photon. Now, we don't see this in the laboratory because it's such a low energy transition that if you will, the atom is in no hurry to make it. It's not particularly energetically favorable to drop to the lower energy. It's favorable, but not super favorable. And so it turns out that the lifetime of the upper state, the average time for the transition to occur, is around 11 million years. And that means in the lab you're never going to see it. You get a bunch of hydrogen atoms that you managed to put in the upper state, or that a collision happens to have knocked it into the upper state or whatever. Well, just wait 11 million years on average and you can see that transition. On the other hand, when we're looking through the interstellar medium, there's lots and lots and lots and lots of atoms there. And as a result, you get to see it. Because the thing is, the other thing I should mention in the lab, what definitely keeps you from seeing it is, well, the atoms are constantly colliding with one another. And the collision can cause the transition without producing a photon. So in the lab, they collide too often for you to be able to see the transition. In the interstellar medium, where There's lots and lots of hydrogen, and the density is way lower. The mean time between collisions is a lot longer. It's, okay, on the order of hundreds of years, which isn't 11 million years, but long enough that you do get, with that many hydrogen atoms, some of these transitions occur. And so as a result, we are able to see some 21 centimeter radiation from hydrogen clouds, H1 clouds in the interstellar medium. And when we do that, that's one of the things that allows us to map what our galaxy looks like from the inside, because interstellar dust says that at optical wavelength we can't see across the galaxy. We can only see out to around 10,000 light years. Our galaxy is about 100,000 light years across. We can't see across the galaxy at optical wavelengths. On the other hand, the 21 centimeter radiation is so long in wavelength, it goes right through dust clouds. And so we can see 21 centimeter radiation from atomic hydrogen clouds throughout the galaxy, from one edge to the other. And by analyzing their Doppler shifts, we can distinguish clouds from one another. The galaxy is rotating. When we talk about the galaxy as a whole, we'll say more about this, but the galaxy is rotating. And so when you look along a given line of sight, you're seeing clouds at different distances, which are moving at different speeds because of the rotation of the galaxy. And so their different Doppler shifts can allow you to disentangle them from one another and see radiation from individual atomic hydrogen clouds. It's easier with an external galaxy. This is spiral galaxy M83 in visible light. Number 83 on Charles Messier's list of things that are not comets. Here it is at 21 centimeters. So this is a map of 21 centimeters wavelength. You can see that the H1 clouds are in fact concentrated along spiral arms of the galaxy. That's something that we'll talk about, why there are concentrations of star formation and clouds and so forth along the spiral arms of the galaxy. So here's 21 centimeter radiation from our own Milky Way galaxy. UR here is indicated right there. And again, this has to be inferred. It requires a model of the galaxy's rotation and disentangling the Doppler shifts of clouds along different lines of sight. There's kind of a blind spot because these guys are all moving almost perpendicular to the line of sight. And so you're not seeing a strong Doppler shift, and so it's hard to disentangle them from one another. So, but in the rest of the disk, turns out that we can do a pretty good job of mapping them, and this is one of the ways that we map the galaxy's spiral arms, is we assume that, like in other galaxies, we don't have to assume that, but in other words, we see the spiral structure of our galaxy when we make these maps, and it's similar to what we see in an external galaxy like M83, for example. Okay, any questions? Ow. All right, so let me zoom out for our viewer at home. Studies of diffuse H1 clouds. Actually, did you guys write anything down about the lifetime and stuff like that, or should we get that into the notes? Like the lifetime of the state being 11 million years and all that. All right, let's put that in the notes then. So, lifetime of the upper state. So, okay, well, let's put it this way. Proton and electron spins can be parallel, higher energy state, higher energy, or anti-parallel, lower energy. photon emitted in transition has lambda equals 21 centimeters, very low energy, that's a very low energy photon. Mean lifetime is around 11 million years. So we don't see it in the lab. Since collisional de-excitation will always happen first. Collision that causes a de-excitation, then generally instead of emitting a photon, it just shows up as a little bit of extra kinetic energy after the collision of the two particles. In the ISM, collision time scale is a few hundred years, long enough that some 21 centimeter radiation is produced. So if we ever took a field trip to the National Radio Astronomy Observatory with the Astronomy Club, we could use their 40-foot telescope that operates at 21 centimeters wavelength. And it's actually very old, so it's hooked up to a chart recorder. At least it still was the last time I went there and did this with students back in '05. And so you can point it at things, and if there's a stronger signal, the chart recorder pen goes up and then goes down as the object sweeps across the field of view of the antenna, because it's just a transient telescope basically. So if I recall, so you just sweep it along the meridian and wait things to drift in and out of its view. Yeah, so anyway, studies of diffuse H1 clouds imply the following parameters. Temperature is around 30 to 80 Kelvin. Very chilly. Makes our recent cold snap seem like a hot heat spell. Heat wave, yeah, that's right. Number densities on the order of 100 to 800 per cubic centimeter. So I'm not putting these in SI, I'm putting it per cubic centimeter because there's 1 million cubic centimeters in a cubic meter, and so I could say 100 million to 800 million per cubic meter. That doesn't mean much to me. It means more to me to say 100 to 800 in a cubic centimeter. That's enough right to get a handle on in a cubic centimeter. So I'm going to just give the densities in CGS units here, typically. 100 to 800 hydrogen atoms per cubic centimeter. The total mass of the cloud around 1 to 100 times the mass of the sun. And sizes of these clouds from around 50 to 150 parsecs across. But you shouldn't think of them as spherical blobs. They're actually very messy. The ISM, in terms of the diffuse H1 clouds, is well stirred, if you like. And so they're not these nice, discrete spherical things. They are not spherical. Instead, they are twisted into long filaments, flattened into thin sheets, or tangled into chaotic shapes. So it makes it's good for aesthetic appreciation, I would say.
Oh, yeah.
Yes. I don't remember if I just lifted that from the textbook, that wording. I may well have. I somehow don't think that I just put it that way myself in a burst of poetry or something like that. Instead, they are twisted into long filaments. Flattened into thin sheets. Sounds like we're cooking, almost. It's like we're making pastry. And now I want some pastry.
I mean, coming up for first break. Grabbing some from there.
That's true. One could not run. Or tangled into chaotic shapes. I don't pretend, now that one's not making me so hungry. I'd like a chaotically shaped pastry, please. Those are the ones that end up in the bin where it's like marked down.
Good stuff.
And these H1 clouds comprise around 1/4 of the ISM by mass. That's in our galaxy. It varies some from galaxy to galaxy. About 1/4 of the ISM is these H1 clouds. There's a little table over there from an intro astronomy textbook mentioning the H1 clouds. Notice the numbers are slightly different. That's because these are the kind of numbers that are just kind of rough estimates anyway. So they're about the same, but not quite what I said before. Okay, so between H1 clouds lies the intercloud medium. I'm just going to say this all and then we'll write it out. The temperature is about 1,000 to 10,000 Kelvin, so it's quite a bit hotter. The density, however, is only about 0.01 particle per cubic centimeter, so the density is much lower. It's in pressure equilibrium with the H1 clouds. If the temperature is higher, the pressure's got to be lower because the pressure, remember, is nKT, where n is the number density and t is the temperature. So if these are to be in pressure equilibrium, the denser part has to be at a much higher temperature, a lower temperature than the less dense part. H in the intercloud medium is mostly ionized because ultraviolet photons from distant stars ionize hydrogen atoms, but the low densities imply long recombination timescales. In other words, very low density means photon comes along, splits an atom apart. If the density was high, the electron would quickly find a bare proton that had also been ionized, and they get together and make an atom. but at these kinds of densities, the reionization timescale is long enough that you have a considerable level of ionization. And he's got, the intercloud medium is about half the mass of the ISM total. So let's write all that down. Woo! Between H1 clouds is the intercloud medium. Maybe like the name of a band. My wife and I, our band name we came up with, not actually made, it was Big Time Steve. So, 1,000 to 10,000 Kelvin, but number densities of more like 100th of a particle per cubic centimeter. In pressure equilibrium with the H1 clouds. Otherwise, the H1 clouds would be shrinking or expanding as a result of pressure put on them by the intercloud medium, or vice versa, pressure, force. I'm going to call it, I don't think it's an official name, but I hereby call it the ICM, because I'm tired of writing intercloud medium. H in the ICM is mostly ionized. By UV photons from distant stars. Low densities imply long recombination timescales. And about 50% of ISM by mass. And square cut.
Intercloud ballistic ICM.